Well, good afternoon, all. It's Rob here again, and welcome to episode 4 or part 4 of this hydronics training tutorial that I'm doing. It's free for anybody that wants to do it on my YouTube channel. So hopefully I'll get some more subscribers if you're all into this. Today we're going to talk about the fabulous IMI app. I'm going to get it all set up with you, and we're going to go through the mass flow calculations on this. We'll start talking about pump sizing and some index circuits, and what I'll do is I'll finish it as we get the explanation of index circuits, but then we'll on the next episode of this tutorial slots, I will go right the way through an index circuit calculation with you, and this is something you can do on your own house, and obviously or any building that you care to do. So we'll move forward with this, and hopefully we can get everybody up to speed at the same time. So a couple of things that we need to do. First of all, if you haven't downloaded the IMI-Hydronic app already, here are the barcodes, QR codes that you can literally scan straight away and get that and get it, or you could just go onto the store and download it. It's a free app, as we've said. So download the app, and then once we've downloaded the app, we will now set it up to the UK settings, but obviously this can work in any country that you're at. I will be setting it up to UK settings. If you set it up the same as me, then that's fine. It will still give you the same figures, and it's only about units really and that sort of thing, depending on your country. Obviously, if you're listening from the US, for argument's sake, it'll all be imperial, but here we're working in metric and those sort of things. But say it's only really units, so you can work out what you need. So if we bring up the app that we've got here, first thing we need to do, and mine is an iPhone, and you can see on the left-hand side here, this is the iPhone, an Android phone, and obviously what first thing we need to do is choose the region that you're at. So on the iPhone, you would click on More, and you can see that at the bottom there, it's got the region as being the United Kingdom. So the next page, we need to go to More again and Settings. So we've got More on your iPhone and Settings on the Android phone. Need to go to those settings. And then the next stage that we do, we need to start changing. So we need to go to Units, and you can see the units. Now what I'll do is I'll spend a bit of time here now going through these, but you can see the main ones that we want to focus on are just here. All right, so we will have a look at these, but I'll go through them all one by one with you, and we'll just make sure that everybody's got exactly the same settings. If you don't have exactly the same settings, there will be a problem and you'll get different results, which is not what we want to do. As we're all playing with this now, we want to make sure that we're getting exactly the same results. So you can see we go to Units, you click on Units, and then this page will highlight up. So this is the way I work. Now you can work in whatever kind of units that you like to do, but for this particular tutorial, I'd like everybody to kind of do exactly the same, so we all get exactly the same answers as we move forward from our heat loss calculation that we had of an uninsulated house of 22.3 kilowatts. So we're going to work on that just on this basis. So I want everybody to just make sure that you've got exactly the same as I've got written on the screen. So for argument's sake, now we've got our pressure is in bar, and if you need to change it, you would just click on it like that, and then it comes up with a little drop down menu, change to what you want. So the pressure we want on bar. Differential pressure we want in kPa, which is kilopascals, and I'll speak about kilopascals in a little while. It's just a little bit more accurate, if you like, than using bar, millibar, or millimeters H2O, that sort of thing. So this is what I prefer to work in with is kPa, and pumps are sized in kPa or meters head, that sort of thing. So I just want to work with that. This is a very important one. We want to be putting it into pascals per meter. Flow. Again, you can do what you like. Litres per second. Obviously, a litre is the same as a kilogram. So a kilogram per second or litre per second is exactly the same thing. But you can do litres per minute, litres per hour, all sorts of things like that. Various different designers and stuff work on different lines. I work in litres per second. And if we can all do that just for this one, you can change it at a later date when you like. Your valve coefficient is, we work in metric, so we want kV. You've got kV ratings and you've got CV ratings. CV ratings are imperial, kV ratings are metric, and I'll do a whole video just on kV ratings of valves, but that's going to be a while. Temperature, again, we want it in centigrade. Yep, for the UK, what we're working in the UK, you can change it to Fahrenheit, you can change it to Kelvin, whatever it is that you want to do, that you prefer to work with. Energy is obviously kilowatt hours for us. Power is in kilowatts. Length is in meters. Diameter in millimeters. Roughness, the roughness of the pipework in millimeters. The thickness in millimeters. Very important one here is velocity at meters per second, as I'm saying over here with these 6 crucial ones as far as I'm concerned. Velocity in meters per second, area in square meters, volume in cubic meters, mass in kilograms, density in kilograms per cubic meter, kinematic viscosity is in meters squared per second, dynamic viscosity in pascals per second. Specific heat, now this is a very, we talked about this on a previous one, this is a very important one that you choose this one. We want kilojoules per kilogram Kelvin, just as it's showing there. Kilojoules per kilogram Kelvin. Thermal conductivity, well, we know what that is because we did that in the first episode of heat loss calculation, so it's watts per meter Kelvin. Heat transfer, as we know, which is our U calculation, which is watts per meter squared Kelvin. And our water hardness is in, I choose parts per million, but again, you can choose whatever you like on that. Forces in newtons, torque in newton meters, sound pressure level in dB. And that is it for that page. So the next page that we need to go to is technical parameters. So back to your main menu and we go on to technical parameters. And this is something that we need to, again, copy everything that I've got written down here. And again, I'm working from SIBC, and you can see what we've got here. So we're looking at SIBC state between a target linear pressure drop of between 300 and 500 pascals per meter. What I want to do is make sure that we get as close to the Goldilocks zone, if you like, of 300 pascals per meter of pressure loss. So I make sure that we've got a target and a maximum linear pressure drop of 300. Every design that I do, and this doesn't matter whether it is heating, whether it's hot water services or cold water services, mains water services or anything like that, I design all pipe work to my Goldilocks zone is 1 meter per second. SIBC stay between 0.5 and 1.5. As I say, I want to try and get closer to the Goldilocks zone of 1 meter per second, so I'm just giving that a little bit of tolerance. So I'm saying from 0.9 meters per second to 1.5 meters per second, and we will talk about making engineering decisions on this as we move forward. Very, very important, but this calculator is an absolutely brilliant bit of kit, so I use it every single day. So once that's done, we then need to filter out our pipe filtering, basically, of which pipes we want. Now, again, different countries will use different scenarios and different pipe work. In the UK, I've basically just ticked all the ones that we would use in the UK. So, for argument's sake, the most common that we're using in terms of copper is the Table X copper, EN1057, Table X copper. Table Y copper is soft copper, often microbore, that kind of thing, so we would use that as well. Table Z, haven't seen Table Z for a long time, but if you dig up water mains, you'll occasionally find a big, thick copper pipe work, and that was old Table Z. Don't really see it much, so I haven't included it on this at all. So then we don't need anything else ticked all the way down. You can see some of the US stuff there. So whatever you're using, just filter out what you don't want. So in the UK, we'll use GFPE, and you can see that I've highlighted that and ticked it. We'll use Henco multi-layer, which is MLCP. MAPRES C, MAPRES E, stainless steel, we'll use those. PEX we'll use, so like the PERT pipes and that sort of thing, PEX and PERT. We then got our steel, which is mostly for a lot of you commercial guys out there, but tick all the British standard ones there and the DIN 2440 ISO 65. So all of those you can see that we have in the UK. So, and that is it. So once they're done, your system is set up. Now, what I will just say is that if you're struggling to get these fixtures staying the same on this part when you change them, once you change them, and this only really happens with the iPhone as opposed to the Android phone from what I can see, is that when you change this, sometimes if you scroll up, it will actually revert back to what it was before. So when you've changed something there, you just got to click done, and then once you click done, that's it. It will stay. And once these parameters are set up in the app, they will stay like that forever, basically until you change them. So there we go. So that's all set up. So we can see, and if you remember, we spoke about this on the previous tutorial videos of stating about the specific heat capacity of water at varying different temperatures. Now, we also said that one of the most important things that we need to do is check and set your temperature. So your flow temperature, always set your flow temperature here. You can see that first. Very, very, very important. And as we said, at 55 degrees, the specific heat capacity is 4.183. So let's just test that, and let's play around with that for a little bit while with the app, and let's see. So if we're at 55 degrees, we are at 4.183. But let's see what happens if we change it, and we'll go to, say, a flow temperature of 35 degrees. See, let's have a look now. So now you can see that the specific heat capacity has gone down to 4.179. As I say, in domestic it doesn't make too much difference, but as I explained before, it can make a big difference sometimes in commercial between different sizes of pipework, etc. So if we stay with the, if we go to an older system of 70 degrees and click done, you can see you're up at 4.19 then. If we go to some of the older systems where they were running at 80 degrees, for argument's sake, your 4.197, which is where your 4.22 comes from. So the higher the temperature, the higher the specific heat capacity. Very important to remember that. This is a point now where we need to start using the calculator, and you can see down at the bottom of your app you've got calculator. So we've already set the fluid temperature. Don't worry about the exclamation mark there, that's just about boiling point. Press on the calculator and this page will come up. Now, what we need to discuss here, and I'll just bring up my phone again. What we need to discuss here, if I go onto calculator, you can see you've got 3 calculators at the top here. You've got power delta T, which is your kilowatt hours, and the power delta T calculator, which is the one we're going to be concentrating on at the moment. These 3 here are your ohms triangle. So we did the longhand calculations before, and we wanted to get the litres per second. So this calculator does kilowatts divided by the specific heat capacity times delta T, gives us our litres per second. Now this, you've got 6 options here. You can see, so you've got your flow, power and delta T, and you've got your litres per second, your kilowatts and your delta T down here. So you can see that your flow represents your litres per second, your kilowatt obviously is your kilowatt, and your delta T is your specific heat capacity, because we set that in our fluids, and that's that section of the ohms triangle there. Now you can see what we can do. We can change 2 of the others. Whichever the answer is that you want, you can change 2 of the others, and you can do exactly the same here on this calculator. So if we want the answer of litres per second, if you click the left side of the app, you'll see that the equal sign goes back up there, and now we can do exactly what we were doing before in longhand calculations, but we can do it with the app. So if we remember, we had, I think it was 0.36 litres per second to calculate that, which is representative of our 22.3 kilowatts heat loss requirement that we had from our heat loss calculation. So if we put in there 22.3 kilowatts, and initially we had a delta T of 15, if we remember, then we go click done, and there's your 0.36 litres per second at the top. I can't tell you how wonderful this app is for very, very quick calculations like this. But again, we can play around with it. So we want to now make this, for argument's sake, a low temperature system. And if you remember, we actually we insulated the loft. We changed some windows in that calculation, and we got that 22.3, and with MVHR fitted as well. If you remember, we got that down to just over 6 kilowatts. So it's about 6.1 kilowatts, I think, if I remember rightly. But that's at DT5 then, if we're going to put a heat pump in. So if we change that and we put in, let's just call it 6.2 kilowatts for argument's sake, as our total heat requirement. But we're changing that delta T to run on a heat pump, and we're going to change it to 5. And we click done. Well, look at that. That actually means we need 0.30 litres per second, as opposed to our 0.36 litres per second from 22 kilowatts at a delta T of 15. So this is making now, this can now, if you start looking into the reasons behind this, this can actually state that if we are doing that, a lot of the existing pipework within that property will probably be exactly the right size. if somebody sized it correctly beforehand. And we do know in the UK that we are very, very prone to oversizing pretty much everything. So from boilers to heat pumps to pipework and all sorts of things like that. So the only thing that is going to stand in or stand in our favour here is the fact that previous people have actually oversized pipework, and the majority of systems that you go to are probably already low temperature ready. And the only things that you might have to change are the primary flow and return and possibly the emitters around the place. And as we said, there's two things in heating that you cannot oversize. One is expansion and the other one is radiators or emitters. But again, I'll come on to that in another tutorial video of sizing radiators by volume. So this is quite an interesting scenario. So if we go back to our delta T15 that we had and our 22.3 at delta T15, and we got our 0.36 litres per second, we now need to try and size some pipework for that to make sure that we're going to get it running correctly. And remember, our target velocity was 1 metre per second, and we were looking at our pascals per metre, so our pressure drop along that pipework of 300 and 500 pascals per metre. But we can make some engineering decisions on this, so let's have a little look. So if we go down now at the bottom, you can see, down here, you can see pipes. So if we click on pipes at this, it's going to give us something that is 0.3645 litres per second. So we click on pipes, and you can see one thing that we have to just double check is which pipes you've chosen. And you can see we've got copper pipe table X here, and again from our drop down list you can change that to whatever it is that you want to do. So you can click on that drop down list and you can see that we filtered out on our list. So this is stating our Goldilocks zone, if you like, which was within the parameters that we set within the app, that 28mm table X copper is absolutely ideal for 22.3 kilowatts of heat loss. So we've got 180 pascals per metre, as you can see there in this line. So there's 80.2 pascals per metre. And the target velocity, well, SIBC state between 0.5 and 1.5. We said we wanted our target velocity to be around 1, and we design everything at 1. So this represents an engineering decision that you've got to make. Now this is 628 pascals that this pipe pressure drop is going to be losing at per metre at delta T15. Now what if we had a 3 metre run? So a 3 metre run from the heat source through to, I don't know, a motorised valve. So that would be your primary flow and return. So if it's 3 metres there and it's a flow and return system, it's 3 metres there and it's 3 metres back. But let's move on to the next slide and I'll explain this in a little bit more detail. Now you can see on this particular slide now, we've clicked on the pipes on this one and it's showing 192.6 at 0.67. Now that is basically, I think, because we've changed the temperature, but we'll check that in a second. So you can see what we've got here. So if we go and bring up the app again, we've got 180.2. Let me just move that out of the way, and we've got 192.6 on this. Now I suspect that is because our fluids are at a different temperature, and you can see I forgot to change it there, so it's my fault. And you can see this is what starts to make a difference in pressure drops. So if we go back down to 55 degrees on there and change it, and then we go back to our calculator, which we've got our 22.3 at 15, and then we go back to pipes. There it is. We're just slightly different. So I must have changed something else in here, but we're almost bang on the money with that. So my point is this. SIBC are stating that we allow these pressure drops between 300 and 500 pascals per metre. And of course you have to add those up for the lengths that you have. So if we had, let's talk about this, let's move this over here for a minute and bring up the calculator. If we had 3 metres from the heat source right the way through to a airing cupboard or something along those lines where it splits into either motorised valves or whatever it is that you've got on your system, S-plan or Y-plan or priority hot water, whatever it is, whatever your primary flow and return are, you can just pace it out. And I just pace these out as I'm doing index circuit calculations. You don't need to get tape measures out, that sort of thing. Just pace it out. Most people can walk in like a meter stride. So we need to be as accurate as we can, but not overly, if you understand. So if we've got 22 millimeters that is in there at this present time, and we've got 671 pascals, as you can see there, for every 1 meter of that. We've got 3 meters running from the heat source to the airing cupboard, for argument's sake, and we've then got 3 meters coming back if it's a flow and return. So we add those together, and that means that we've got 6 meters of pressure loss. So if we go onto here and we say we've got 671 pascals times 6 equals, so we've got 4,026 pascals, or 4 kPa on that pressure loss on the primary flow and return. Now, what CIBSE also state is that there are pressure losses through fittings, and we'll come on to the next slide and I'll talk to you about that. So as we said, CIBSE states there's a pressure loss for fittings, and now CIBSE actually states that we need to allow 50% for fittings. Now, as you can see that I've written on the screen here, I don't really agree with that, because I've been doing this a long time and I've never had a problem with sizing pumps in this aspect. And I think this is quite important to discuss at this point. So if we had 6 meters, as we said on our calculator, and we had 6 meters, so we had 4,026 pascals for that primary flow and return, or 4 kPa. Let's just say we have 3 changes of direction with that. So what I suggest and what I state, how I teach this and how I think it's correct, 50% I think is overkill for added pump head that is required, or added pressure loss that is required. So what I do is I just add 10% for every change of direction for both the flow and the return pipe work. So if you've got 2 pipes going up the wall into the ceiling, and then they elbow 90 degrees to go under the floor, heading towards an airing cupboard or whatever, that's 1 change of direction. So you take both the flow and return, that's 1 change of direction. You'll probably find in most circuits that there's going to be less than 5 changes of direction, which would equate to the 50% that CIBSE state. What I would say is that if you've got 3 changes of directions there, you're going to add 30%. So what you can do with this particular calculator, if we want to add 30% or 3 changes of direction to that, we take the number and we multiply that number by 1.3. And that is your 30%. You can do plus 30% as well, but I like to do it this way. So if it's two changes of direction, it'll be 20%, and that'll be times by 1.2. If it's 5 changes of direction, it'll be times 1.5. But you can see, so 4,026 pascals times 1.5 equals 5,233.8 pascals, or 5.2 kPa is the resistance of that entire primary circuit. Now that is something that we have to add up as we go forward, but let's move on to the next slide and we'll start talking about pumps before we start and end this video on index circuit calculations, or we're going to start the explanation of index circuit calculations on the next tutorial video. So let's move to the next slide. Pumps. Very, very important subject, and something that we get incredibly wrong. I've heard a statistic, and I speak about this on many online platforms and that sort of thing, but this is really quite weird and scary when it's described this way. But it's estimated that between 15 and 20% of the world's entire electrical energy usage is taken up by dead-headed or oversized pumps. Now, just think about what that means. That is trillions of pounds, trillions of dollars, if you like, of wasted energy. This is why I have the hashtag wastage crisis, and this is why I keep pushing it all the time, because I do believe that we waste so much energy and it's unaccountable. But if you imagine that with all these dead-headed pumps, and you see them all the time, and you get so many people that don't understand how pumps are and how to size pumps. I've done a tutorial video before on the Grundfos sizing app, or sizing software, which is really, really good. I recommend people have a little look at that and catch up with it. But it'll specify a pump size for you. And you can see here that we had 0.36 litres per second of requirement. Now I calculated out. I did this as an example. You can change this in the software from meters head to kPa or whatever it is once you've calculated an index circuit out. But you put that into the system, and you can see it actually builds a pump chart for you, and it's stating that for our 22.3 kilowatts of heat loss with a 3 meter head of resistance, or 3 meters, or that would be 30 kPa or 30,000 pascals. We have got a pump chart here, which is there. So you can see 0.36 litres is along the bottom axis, and on the head axis up the side here, so there's our 3 meters of head, or kPa, that could be, whatever it is, and there's our flow, 0.36 litres. And there you see, then it gives us our curve. So it's a really, really good bit of kit. What does a 25, 60, 180 pump actually mean? This is something that I've taught and been surprised at for a very long time, that even engineers that have been in the game for a very long time don't seem to understand what pumps mean. Do you think you actually size a pump by the height of a building? Well, the answer is absolutely not. You do not size it to the height of a building, and it's a big misnomer, if you like, that has been spoken about many times, and people have got this so wrong. So the 25 on a 2560 pump is the bore size. The 25 is the bore size. The 60 is 60 kPa, 6 meters, or 60,000 pascals of head resistance that will overcome. Now we remember with our calculation tool that our primary circuit was just 5 kPa or 5,000 pascals. So one of the smallest pumps you can buy is a 1550. So a 15, which means 15 is the bore size, 50 is the 50 kPa or 50,000 pascals, or approximately 5 meters of head resistance. You never, ever, ever size a pump by the height of a building. You always size it to required flow and resistance of the system index circuit. Very, 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 very important to understand. And I'll show you now how when we size a pump, of what the differences can actually make when we move to the next slide. So just watch this, quite interesting. So this was a live project that I did, a live commercial project, and these were 2 fixed inverter pumps that were in on this project. Now this was serving 238 flats, I think it was, up in Stevenage, a little project that we were doing up there. Now those pumps, you can see this pipework coming in on the side here, that is DN 150. So that's quite a large size of pipework that's in there, coming in and out of this unit. That there is a Spirotech dirt separator, obviously all insulated up at this present point in time. They're all dirt separator. Now these inverters, I could barely get my arms right the way around them to touch my hands on the other side. That was the size of them. So you're talking incredible weight. It needed big winches and stuff like that to actually get these out. But I did an index circuit calculation on the project of this, serving 238 flats. These pumps were running at full tilt. They were costing the site an absolute fortune, and all of the pipework downstream of all this pipework downstream, you could actually feel it was rattling the way it was so much velocity running through these pumps. It was causing system erosion, corrosion, all sorts of problems with this system, all because these pumps are over-specified and not properly calculated out. Now in the next slide, and I'll swap between these 2 slides just to show you the difference of what we did when we replaced these pumps, and use this dirt separator here as reference. That dirt separator, I think my head actually came to about that line of that blockwork there. So you can imagine how tall that is there, and I'm about 5'9". So look at this next slide and see what we actually calculated the new pumps that we're going to replace these with. And there's that unit there. So you can see that we've reduced the size down to DN 100 through here, capped off one of these things from these 2 headers either side. So we capped off that first one, the flow's coming in here, straight down into the pump set and straight out. The difference is that replacements of these pumps, in terms of cost wise, the original pumps there, to replace like for like, but with inverters and the installation on it, was nearly £100,000. It was a lot of money to actually replace these. And when we placed these, the actual cost of these pumps that we went in there once we'd done the flow rate and the pressure loss across what we needed, they came in at just over £10,000. So you can see we don't just have a wastage crisis in energy, we have a wastage crisis in monetary terms as well. And doing an index circuit calculation to what you need to get the correct flow rate, and what we're trying to do is we're saying the Goldilocks zone is going to be 1 metre per second. That's what we're after. That system now is running much, much, much better than what it was. There's less velocity running through the pipework. Everything is getting to the index circuit, and there was 4 blocks of flats here, and I'll talk about those on another tutorial video as we move forward. But I hope that you understand why it's so important to get an index circuit calculation correct. And I'll explain an index circuit calculation now before we end this tutorial video and start on the next one. So just to recap, the index circuit, this is the radiator, emitter, heating coil or flow and return to an underfloor heating manifold or whatever it is with its own pump that has the highest calculated resistance circuit back to the primary pump. And that's out of all others on the system. And once that one emitter or valve, I've found index circuits to be a valve that's right next door to the pump, because the valve has actually got a very high kPa rating, and it's once it gets over that resistance, it will get over the resistance of everything else. And this is where people often get it wrong and oversize. So we only need to find the resistance or the kPa of the highest resistance within that circuit. And there's many circuits, but we'll come into a lot more detail on that as we move forward. But this is how I would describe an index circuit. So I drew out this very quick drawing in my software. For anybody that ever wants to know, I use Vectorworks because I use Mac, and I do all my drawings through this. But imagine we've got a length of 28mm pipe there, you can see, coming out of a cold water storage tank, and it's boosted. So it's got a booster pump on it, and it's pumping along this length of pipe. Now this length of pipe doesn't matter if it's 10 meters long or 10 miles long. It doesn't make any difference to that at all. We've got a static height, as we said, of 6 meters or 60 kPa. We know that if that 60 kPa pump can get water coming out of that point there as a pyramid, which is the highest point, we know logically that it will always come out of these pipes because they've got less resistance. Now that is your index circuit, and whichever the biggest resistance could be, so if that was, for that argument's sake, had 65 kPa resistance on it, that would be your index circuit and not that one. And that could be a valve that causes that. But we know that if they're just open pipework right the way through, it doesn't matter if there's 6 aside like what I'm showing there or 60 aside, it doesn't matter. So that could be 10 miles long or whatever it is. As long as it comes out of that one at the top there, you know it's going to come out of all of the others. That is the best explanation of an index circuit I can think of. If you can think of anything else, put it in the comments and see if we can move it forward, and I'll do a short on that if you think you've got a better explanation. But that's the way I try to visualize it, and I think that was very, very helpful to engineers to understand. All you need to do is overcome the resistance of that one, and it'll get over the resistance of all of these, whether there's 6 aside here or 600 aside. It doesn't matter. So whether you're in a 2-bedroom flat, for argument's sake, with 4 emitters or something like that, or in a 200-bedroom hotel with 2,000 emitters, it makes no difference. As long as you find the index circuit of which is the highest resistance, that was how you would size your pump. That is it. End of story. So in our previous slides, we suggested that we needed 28mm primary pipework, as we stated. But as we talked about with this, and we've sized it, and we found out that we got this 4,001 pascals. Would you actually change that 22mm pipework that is already in existence, or would you start ripping floors up and charging the clients more? This is where you have to make an engineering decision, because we've only got 4 kPa of resistance running right the way through the system. So this is really quite important to get this correct and understand this index circuit calculation. And what we'll do now as we move forward, so we can see that we could actually make that engineering decision and leave the 22mm pipework in place, even for Delta T5 system at 6 kilowatt, as we've proven. So I'll leave this tutorial video at this point, but this is what we're going to be talking about next time. And this is a typical 1-bedroom property that has just got 6 emitters in it. And we'll talk about this, and we'll talk about how we'll calculate the index circuit of these as we move forward. So I really hope you enjoyed this tutorial video, And if you did, please give it a thumbs up, subscribe to the channel, and get more people viewing, which would be great, and that will help me out. And obviously we can move forward. I have been getting a lot of requests and a lot of comments and private stuff and all sorts of things like that, which are taking up a lot more of my time. Now, I don't mind doing these tutorial videos for free. I think it's it's a good thing, and I think it's helpful. What I might do though, and this has only happened in recent, I wasn't planning on particularly doing this, but I might set up a little GoFundMe page or something like that. Then if anybody's feeling any generous for a couple of quid or whatever it is, then you're very happy. Or I'd be very welcome if you put something through that, and that is literally just to kind of cover some costs. That's all. But bless you for watching, everybody, and I shall see you on the next one. Many thanks. Goodbye.